I'll start by thanking the organizers for inviting me to present to this meeting. I wish I could be there with you. I've been exploring Mars robotically for about 30 years, and this gives me an opportunity to consider how human exploration of Mars might benefit the scientific exploration of Mars, most especially the exploration for life. The most profound question we can ask about Mars is whether there is life or ever was life there. And so now I'm going to try to pursue this question of how human exploration might benefit that search for life. I'm going to start with some context, and a figure I really appreciate is this concise version of the exploration of Mars since the early 1960s. And it's a little out of date, so I'll add that China and UAE have also recently been exploring Mars. So there's decades worth from the early 60s onward, and many of these missions failed to reach Mars. Others either flew by, went into orbit, landed, and even roved throughout this decades of Mars exploration, robotic exploration. And one of the first, really the first successful mission to Mars was a flyby by NASA in 1965. And it gave us the first close-up images, even though fairly low resolution. We got television camera images of the surface of Mars, which for the first time actually revealed craters, which are not visible through telescopes from Earth. So this was the first close-up image of Mars, giving us a sense of Mars as looking more like the moon with craters. The second set of flybys in '69 gave much better, a factor of 10 better resolution, but still were revealing pictures, images of the surface of Mars as a crater-covered planet. Again, much like the moon as we knew at that time. So this was somewhat, I suppose, disconcerting to see that Mars wasn't the kind of planet maybe that had been hoped for or speculated on. It took the first orbiting mission in 1971 by NASA to start to give a better sense of other features of Mars. In this case, this is a huge channel, hundreds of kilometers long, and scientists concluded that this was likely formed by flowing water, in fact, catastrophic outflow channels. So this turned out to be now an emerging view of Mars with a range of landscape features, including craters and channels and other features indicative of water. In '76 was really kind of one of the high points of Mars exploration with the NASA Viking 1 and 2 orbiter and lander. So two of each, they were flown as a redundant set to ensure one pair succeeded. And inside of this shell here is a lander. So this was the first time a lander was sent to the surface of Mars. And here's a full-scale mock-up of that lander, and it's showing Carl Sagan for scale. He was involved with that mission back in the day, and there was still hope that Mars might harbor life, perhaps some form of hardy life like lichens maybe on growing on rocks. But those first views from the surface pretty quickly dispelled the idea that life was going to be seen visibly. But this mission was equipped with both landers at two different places were equipped with scoops, with an arm with a scoop that could bring Martian regolith or soil onto instruments on board. Arguably the most important of which, at that time anyway, was this biology experiment, which was really three different experiments built into this very small volume. And here's a simple diagram of those different experiments: the pyrolytic release experiment, the label release experiment, and the gas exchange experiment. both the gas exchange and the labeled release experiment actually gave positive results that were indicative of microbial life. Most provocative was the labeled release experiment, which had a very high signal that interpreted alone would have been positive evidence for microbial life. But a fourth instrument, the gas chromatograph mass spectrometer, was able to look for organic molecules. And in this case, it detected only a very small, essentially below the detection limit for organic molecules of any kind, except for the organic cleaning solution at very low level that was used to clean or sterilize the system. So in this case, very, very little evidence for organic matter here, despite the evidence from the other instruments. So collectively, most scientists on the team, and really since then, have concluded there's a consensus view that that lack of organic detection likely means there is no extant life in Martian soil. And then I leave the but question unaddressed, which is there's really still a lot of controversy about what that might mean, those positive detections, especially knowing that there's an oxidant in the soil of Mars that may be responsible for the destruction of organic matter in the gas chromatograph mass spectrometer apparatus. So it's a still open question. But this was enough for NASA to essentially abandon the strategy of searching for extant life in favor of searching for ancient life that may have existed, extinct life that may have existed on Mars in the past. And so it started this strategy of following the water on Mars, looking from orbital data, where are places where it appears that water could have existed on Mars in its ancient past. So the first set of missions following Viking were really an effort to follow through on that approach, follow the water. And then as exploration matured and successes from those earlier missions definitely were showing evidence for a watery ancient Mars, later missions started to explore for habitable environments beyond just the presence of water. Habitability is key, as well as preservation of potential life that may have existed in those potential habitats. And then finally, we're sort of in the era of seeking signs of life, especially with the Perseverance rover that I'll talk about a little bit more in a minute. And through all of this is this idea that each of these missions has the potential, at least several of these missions had the potential to help prepare for human explorers in the future. So the Perseverance mission is part of this sample return campaign. Something that has never been done from Mars is the return of samples. So this campaign involves the first mission in the series is the Mars 2020 or Perseverance mission, which is all about collecting rock samples, small cores, about finger-sized core samples of carefully selected rock samples. Roughly 20 to 30 of them will be collected and stored both on the rover and in a separate cache, a depot, where if the rover can't deliver the samples, the return retrieval spacecraft can go get them. And I'll now go to that one. So the second phase of this mission is to, again, send a retrieval lander that includes a Mars ascent vehicle, a small rocket that can carry the samples to orbit. And the plan currently is to use Perseverance to deliver samples to this retrieval lander, and we'll use an arm to put those samples on board the rocket. If the primary means, the Perseverance rover, is disabled, it will have 2 Ingenuity-class helicopters to go retrieve samples from the depot that I mentioned a minute ago. And the third component of this third mission is an orbiting spacecraft that will pick up the from the rocket will carry the samples inside a small container, roughly a basketball-sized container, and this return satellite will pick up those that cache, or that orbiting sample is what it's called, and return it to Earth, and which it will then be sent to the surface of Earth without a parachute, hard landing, to be collected in the Utah desert. So it's a big campaign, hopefully returning by 2033 is the current plan. This Perseverance mission went to a very carefully selected site. It was competed with a few dozen other sites over the course of 4 years or so to find a place on Mars that had the best potential for a habitable environment that could preserve evidence of potential biosignatures if Mars ever had life. So Jezero Crater and this beautiful delta, you can see here, it's an eroded remnant of an ancient delta with a channel flowing into Jezero Crater is the rim here. And so this was the place that was chosen from a long list of possible sites, again, with the idea of maximizing the potential to sample preserved microbial life if it was present. And this mission also included preparation for human explorers in the form of this MOXIE instrument for in situ resource utilization. The MOXIE instrument is on board, as you can see in this blue outline here, and it's intended, and it has successfully now drawn in and compressed Martian atmosphere, which is dominated by CO2, and extracted oxygen, pure oxygen, from Martian atmosphere at the rate of roughly 5 grams per hour. And so this is an instrument that has now proven for the first time that ISRU, in the form of extracting oxygen from Mars atmosphere, does indeed work. It's energy intensive, but it's conceivably doable if this were scaled up to a much larger unit or multiple units, that this could provide breathable oxygen and even O2 for fuel in the return rocket. Another feature is essentially in preparation for human explorers is to return Martian regolith, some amount of soil from which in a return sample, the characteristics of the globally homogeneous dust on Mars could be assessed for potential health hazards. This is a conceivable issue that there's something about the dust, either in the form of the particles or even the composition, that could be a health hazard. So before astronauts go, ideally, Martian dust would be assessed for whether it's a health hazard. A return sample can also be tested for extant life. I spent a few minutes talking about the potential that, it's a low potential, low probability, but perhaps there is extant life in Martian soil. So all of the samples will be tested, but the regolith sample will be best, probably the most likely place for extant life if it exists on Mars. So these samples returned to Earth will help with preparing for human explorers. But then it becomes the question of where to go. The robotic exploration of Mars, as I'll say in a minute, has been constrained by various things. In this case, human exploration really is going to be constrained to where there's water, and really what this means is where there's water ice. And so we have information. This was a really great result from an earlier mission. The Mars Odyssey mission carried a neutron spectrometer that could essentially map out, and this is a global map spread out, and it could map out where hydrogen is present in the surface and subsurface down to about a half a meter or so. And so this map really is, by the time you get to these intense, by these intense blue colors, really, there's so much hydrogen there that the only phase, the only material it can represent is H2O ice. Other places could be water bound in minerals, but these intense blue colors are so hydrogen rich that they really have to represent water ice in the near subsurface, less than half a meter down. And there was a mission in 2008 called Phoenix that went to essentially test that observation. Is that a place that has shallow water ice? And you can see this in this rendering. There's retro rockets that lower the lander to the surface. And the scientists during that mission were thrilled, as we all are actually, to be able to look underneath that lander where the retrorocket blast had blown away regolith to reveal basically pure ice. So this was a remarkable accomplishment. And of course, there was a scoop and an arm with a scoop on it that could dig down. And so you're seeing a trench dug by that scoop. And you can see just even a few centimeters down in this regolith are patches of water ice. And my cursor, there's water ice in the floor of this trench that would slowly sublime over the course of days. And so it was clear evidence, and even it was able to be brought on board to test. So this is absolute ground truth for that hydrogen mapping. So we have good confidence that there are places in the shallow subsurface in the regolith of Mars that have abundant water ice for future explorers, ideally. And there's other ground truth from recent impacts. Spacecraft have been able, in orbit around Mars, have been able to identify the occurrence of new impacts. They typically are very small. You can see all of these are less than 20 meters. All the scale bars are 20 meters. So some of these are just 5 or 10 meters across. And these recent impacts in some places expose very bright white material that then goes away over the course of days or weeks. So it's very strong evidence that this is water ice. And some mapping, this is the most recent example of mapping of these recent craters, some of which don't show ice, but in high latitudes, many of these recent craters, small craters, show evidence of ice. And note that this mapping only goes into the high latitudes, because below about 35 degrees, no icy craters have ever been observed. By the way, it's in part, there's a bias toward dusty places because they're easier to spot from orbit, where there's a new impact which reveals a dark spray of material from underneath the bright dust. So there's a bit of a sampling bias, but there's still pretty clear indication, as this figure shows, that these icy craters, which are shown in blue in this figure from Dundas et al., shown in latitude versus size, and they're all essentially below 25 meters in diameter. There's kind of a cutoff, although a brand new result in the last less than a year is down to about 35 degrees north latitude. But otherwise, most of these icy craters are in high latitudes above 30-something degrees, both in the north and southern hemisphere. They're mostly in the northern hemisphere, though. And this is just for comparison to some of the constraints on robotic exploration. In this case, the most recent mission, the Mars 2020 lander rover, was required to land within this box of 30 degrees north and south because of thermal limitations. Essentially operating the rover above 30 degrees, either north or south, was deemed too much of a engineering challenge to keep those keep the equipment warm enough. So this is sort of typical of robotic exploration. And it does kind of point out that human exploration will also have to deal with these much colder places in high latitudes. So it will still be an issue if human explorers are going to high latitudes where there's ice. But human explorers going to ice offers the potential of searching the ice for life. Now, there's a proposed mission concept here, the Mars Life Explorer, that is a robotic mission, potentially will be flying in the next decade. It's part of the NASA's decadal survey as a concept anyway. And so this is an example of going intentionally to an icy place on Mars in the hope of, well, searching for life in an icy environment, with the assumption that the ice, maybe through thin film liquid or other times of the Martian orbital cycles, that there could be liquid water that could host life. So this mission is intended to go to a place like this, but humans may also be going to a place like this. So that's the question here is, if human explorers go to an icy regolith place, will they be able to aid in this search for life? So this is a couple of slides from a report from this group, the Mars Exploration Program Analysis Group. It's a community, sort of JPL-led community effort that's been around for decades now. And so the MEPAG committee essentially assessed, this is a recent meeting that they attended, at least some members attended and gave this presentation, trying to address whether there's 4 different major goals of the MEPAG goals document, and where in what parts of those goals and objectives can human exploration benefit. So I'm not going to show all of that, and this is an eye chart, obviously, but the intent is to sort of demonstrate that one of the goals, goal 1 of this MEPAG goals document is, as it says, determine if Mars ever supported or still supports life, and there's all these objectives and sub-objectives. And this recent evaluation essentially went through and established whether humans benefit these particular goals and objectives. And in many cases, the answer was yes. There was high potential benefit of having humans involved with the exploration for life on Mars. And so I'm going to conclude with what they concluded in their summary of findings here, and I'll probably sort of read through these in some detail. This first bullet, this group established that for no investigation was human presence detrimental, even goal 1, the life goal, considering trades between human skills versus contamination. So this is an important result that, there still are people who think that introducing humans into the Martian environment will contaminate it in a way that will be detrimental to the exploration of either extant or extinct life. But this group evaluated the potential, and I think it's a sort of legitimate view that certainly humans can, for example, on Earth, control contamination in field sample collection environments where scientists are interested in, for example, DNA. Humans in the field can control for contamination. So I think this is a good result that suggests human exploration will not necessarily be detrimental to human exploration of Mars for life will not be detrimental. I think that these other points are all really valid and good, that humans certainly will be able to select better samples than a robotic mission. It's very cumbersome to select samples with a robot, so humans are likely to do a better job. And there will be sample degradation before they return to Earth, the ones that are going to be brought back robotically. There likely will be some amount of degradation as they're going through all of the steps to reach Earth. So humans there can analyze samples before they're degraded. The human crews will need to return to Earth, which is likely to mean a larger sample mass can be returned along with the humans. Deep drilling absolutely will benefit from having humans there versus the cumbersomeness of doing it robotically. Humans can also deploy various instruments more favorably than robots. And they concluded that there's a lot of overlap between the highest science priority investigations that the MEPAG community wants to see, and that will be aided by human explorers. So their conclusion, and I concur, that human explorers can significantly help further fundamental Mars science. And I think in particular, the search for either extant or extinct life will benefit from humans on the surface of Mars. So that's all I have. I wish I could take questions. I would be happy to take your questions by email. If you have something really burning that you'd like to reach out to me, I'd welcome your email questions if you'd like to. So that's it for me. I hope you all have a good meeting, and thanks for listening.